In this video, I am going to describe about push-down automata PDA. PDA is a 7-tuple machine. M is equal to Q, sigma, del, tau, Q naught, Z naught and F, where Q is the finite set of states, sigma is the finite set of input alphabets, del is the transition function, tau is the finite set of stack alphabet, Q naught is the starting state of PDA, Z naught is the initial stack symbol, F is the set of final states, and Q naught belongs to Q, Z naught belongs to tau, and F is the subset of Q. Now we see example for designing a PDA when the language will be like L is equal to 0 power n, 1 power 2n, where n is greater than or equal to 1. The first step is to obtain a language by substituting n is equal to 1, 2, 3 and so on, and the language will look like this. The language consists of 0 at the first and then only 1 comes. So the initial transition starts from Q0 to Q1 with the input 0. When 0 comes, it is pushed into the top of the stack, and the same should occur for all the other zeros. Once all zeros are completed, 1 will be reached. For the first one, nothing is to be performed, and the stack symbol 0 is retained. And when the second one comes, pop the 0 present at the top of the stack, since the stack follows last in first out principle. These steps are to be performed continuously until the blank is read. So add a transition from Q3 to Q2. Now the required steps are performed simultaneously until the blank is reached. And when blank is reached, the PDA enters into the final state. The next step is the transition of PDA. Let us consider an example of this transition for writing this PDA. The current state is Q1. The input symbol is 0 and the stack symbol is also 0. For this kind, the transition retains in the same state and the 0 is pushed into the top of the stack. So the operation performed here is push 0. So the right corner of this table informs the operation performed. Likewise, all these transitions are filled and finally accept state is reached. The next stage is validity checking. In this stage, consider a valid string and an invalid string. For the valid string, the PDA should enter into the acceptance states, and for invalid string, the PDA should stop at one position where there is no possible transition to reach. And the transitions are: first 0, the 0 is inserted into the stack, and for all the accompanying zeros, the same is performed. And when 1 comes at first, nothing is to be performed. So what? We have retained the stack symbol 0 as such. And when the second one comes, the 0 is to be popped out. So what? We have popped 1 0 when the second one comes at this stage. The same operations are performed, and at last the input symbol becomes blank and the stack contains the initial stack symbol. So the PDA enters into the final state, which is also known as an acceptance state. At last, the valid string is processed by the PDA, and for an invalid string, W is equal to 0, 0, 1, 1 and B. In this, the number of zeros and ones are equal, but for a valid string, the number of ones should be twice that of the number of zeros. So this is surely an invalid string. Let us process this now. For this, the first 0, it is inserted into the stack, and the second 0 is also inserted into the stack, and when first 1 comes, nothing is performed. And for the second one, the 0 is popped out, and here the PDA stops with no transition. So the invalid string stops when there is no possible transitions at all. Thus the PDA is designed successfully. Thank you for listening.